Bismillahirrahmanirrahim. Assalamu alaikum. Welcome to the online data structure class. What we will be doing today is to start the second online lecture on chapter 7, which is on sorting. Let's take a look at an example on slide 18 in the previous lecture 1, where an array contains the data elements in the following sequence: 81, 94, 11, 96 up till 15. Some of the last 5 sort sequence were missed in the last lecture. So let's redo it. We have 13 numbers to be sorted. Let's choose shells increment 5, 3, and 1. For the fifth increment or gap, we will look at numbers 81, 35, and 41. Sort in order or swap the values such that we have the numbers as 35, 41, and 81. Then look at numbers 94, 17, and 75. Similarly, swap the values as well such that we have 17, 75, and 94. Then we will look at numbers 11, 95, and 15 and swap the values such that we have 11, 15, and 95 in the array slots. Then we will look at numbers 96 and 28 and swap the values such that we have 28 and 96. Then we will look at numbers 12 and 58, which are already in order. Once finished, we will have 5 sorted array as 35, 17, 11, 28, 12, 41, 75, 15, 96, 58, 81, 94, and 95. And the rest of the third and one gap sort sequences remains the same. A small size insertion sort is quite efficient. On a larger size array, applying insertion sort can be efficient if the elements are already close to sorted order. Before doing the smaller insertion sorts, the elements do get closer in order before the larger insertions are done, which is the rationale of Shellsort. Popular but poor choice for increment sequence suggested by Shell are Shell's increment. Your h of t equals floor of the number of elements divided by 2, and your h of k equals to floor of h of k plus 1 divided by 2. Now let's take a look at an example. So in our example, we have the following numbers in sequence: 18, 32, 12, 5, 38, 33, 16, and 2. 8 numbers to be sorted. Shell's increment will be floor of 8 by 2, which equals to 4. We will look at 18 and 38 and sort in order. 18 and 38 stays at its current position because they are in order. Then we will look at 32 and 33 and sort in orders. Again, 32 and 33 stays as its current position. Similarly, numbers 12 and 16 will gonna remain same. Numbers 5 and 2 needs to be swapped because they are not in order. Once done, the resulting number after the Shell's increment of gap 4 will be 18, 32, 12, 2, 38, 33, 16, and 5. Now further, shell's increment will be floor of 4 by 2, which equals 2. We will look at numbers 18, 12, 38, and 16 and sort in order, which will be then 12, 16, 18, and 38. Similarly, we will look again at numbers 38, 2, 33, and 5 and sort in order, which will be 2, 5, 32, and 33. Resulting numbers after increment of gap 2 will be 12, 2, 16, 5, 18, 32, 38, and 33. Further, the shell's increment will be floor of 2 divided by 2, which equals 1. The last increment or gap of shell sort is basically an insertion sort algorithm. Then the resulting number after the increment of gap 1 will be 2, 5, 12, 16, 18, 32, 33, and 38. Let's observe a snippet of shell sort code taken from the book. Here in the implementation, function name shellsort accepts two arguments, variable a and n. Variable a is an array of type element type. Element type is typedef to an integer. Variable n is of type integer. Inside the function, you have variables I, j, and increment declared as type integer. Variable temp declared as type element type, which is an integer. Next, you have a for loop where the variable increment is initialized equal to n by 2. Then increment up till the floor value of increment divided by 2. This for loop will be taking care of shell sequences. Next, you have a nested for loop under the sequence for loop, whose variable I is initialized equal to increment. I is less than number of elements n I plus plus. Since you will be swapping the elements, you assign the element from array A index I to temp. Next, you have the inner for loop where variable type integer j is initialized to I. J is greater than or equal to increment. For loop iterating with j by being decremented as j equals j minus increment. You have an if-else condition where if the temp variable is less than array index j minus increment, then we proceed with assigning array index j to array index j minus increment. Else the inner for loop breaks and array index j is assigned the temp variable integer value. The runtime for shellsort depends upon the choice of increment sequence. If we pick shellsort original sequence increments, the worst case runtime proved by theorem 7.3 in your book will be order n square. Now if we pick Hilbert sequence increments that are 1, 3, 7, 15 up till 2 to the power k minus 1, the worst case running time of Shellsort, then proved by theorem 7.4 in your book, to be order 1.5. The average performance of Shellsort with the Hilbert sequence increments to be order 1.25. For mid-sized data like elements less than 5,000, Shellsort is nearly as well, if not better, than faster and log n sorts. The next technique that I will discuss is heap sort, the rationale of which is to build a heap of elements that needs to be sorted, then start removing the largest element or the smallest, depending upon the ordering relation, until only one element is left on the heap, and put the element removed into the place vacated by the shrinking heap. We have already been acquainted with priority queues in chapter 6, thus we can use it to sort the elements in order n log n time. Algorithm based on this idea is known as heap sort. Basic strategy is to build a binary heap of n number of elements, then perform n delete minimum operations. Record these elements in a secondary array and then copy them back to the first array. Since each delete min takes order log n time, so total running time is order n log n. Heap sort is in-place sorting method that it uses no extra memory. If the value at the node n is greater than or equal to the value at each of the children of n, the heap is called max heap. Similarly, if the value at the node n is less than or equal to the value at each of the children of n, then heap is called min heap. We have studied how to convert the unsorted array into a max heap. Here unsorted array we have is numbers 46, 52, 28, 17, 3, 63, 34, 81, 70, and 95. After conversion to max heap, we get the elements sorted as 95, 81, 63, 70, 52, 28, 34, 17, 46, and 3. In order to sort, let's delete the maximum element of this heap, which is element number 95. This leaves a gap at the back of the array, which can be filled by the max root number. Now let's follow through pictorially what gets replaced by deleting max root node 95. Number 95 at root node will be replaced by the last leaf node, which happens to be number 3. We delete leaf node number 3 and put the number 3 into root node. Now 3 once at the root node will get swapped by number 81 since 81 is larger than 63. Number 3 once again will be swapped by 70 since 70 is larger than 52. Number 3 once again will be swapped by 46 since 46 is larger than 17. As I mentioned in the previous slide, that the last entry in the array, let's fill it with the largest element, in our case is 95. Now let's repeat the process of delete max operation and then insert the max element at the end of the array. Let's follow through pictorially what gets replaced by deleting max node 81. Number 81 at root node will be replaced by last leaf node, which happens to be number 3. We delete leaf node number 3 and put number 3 into the root node. 3 once at the root node will get swapped by number 70 since 70 is larger than 63. Number 3 once again will be swapped by 52 since 52 is larger than 46. We repeat this process of delete max operation and append 70. Number 70 at root node will be replaced again by last leaf node, which happens to be number 17. We delete leaf node number 17 and put number 17 into the root node. Now 17 once at the root node will get swapped by number 63 since 63 is larger than 52. Number 17 once again will be swapped by number 34 since 34 is larger than 28. We will again repeat the process and delete max and append 63. Number 63 at root node will be replaced by last leaf node, which happens to be number 17. We delete leaf node 17 and put number 17 into the root node. Now 17 once at the root node will get swapped by number 52 since 52 is larger than 34. Number 17 once again will be swapped by 46 since 46 is larger than 3. We again repeat the process and delete max and append 52. Number 52 at root node will be replaced by last leaf node, which happens to be 28. We delete leaf node 28 and put 28 into root node. Now 28 once at the root node will get swapped by number 46 since 46 is larger than 34. We repeat the process, delete max and append 46. Number 46 at root node will be replaced by last leaf node, which is number 3. We delete leaf node 3 and put 3 into the root node. 3 once at the root node will get swapped by 34 since 34 is larger than 28. Again, repeating the process and delete max. Append 34. Number 34 at root node will be replaced by last leaf node, which is 17. We delete 17 and put number 17 into the root node. 17 once at the root node will get swapped by number 28, since 28 is larger than 3. We delete max and append 28. Number 28 at root node will be replaced by last leaf node, which is 3. We delete leaf node 3 and put 3 into the root node. Now 3 once at the root node will get swapped by 17. Finally, we can dequeue 17, insert it into the second location, and the resulting array is sorted. As an homework assignment, go through the source code provided into your book and also in your lab. Our next discussion is on Mergesort and quicksort, that are fundamentally divide and conquer sorting techniques. The rationale here for Mergesort is to recursively sort the left half, recursively sort the right half, then merge the two sorted halves. As mentioned before, Mergesort is based on divide and conquer strategy. We divide the list or array into two smaller lists of about equal sizes. Then sort each sublist recursively. Once done, we merge the two sorted lists to get one sorted list. The fundamental operation in Mergesort algorithm is merging two sorted lists. A merging algorithm is an algorithm that takes two sorted sequences as inputs and combines them into a single sorted sequence. Now let's consider two sorted arrays, upper and lower, as well as a third one, which is an empty array. Let's name the empty array as combined sorted array. The upper sorted array contains numbers 3, 7, 12, 18, 24, and so on. The lower sorted array contains numbers 2, 5, 16, 21, 33, and so on. We will define three indices at the start of each array. We compare number 2 from lower sorted array and number 3 from upper sorted array. Since 2 is less than 3, we can copy number 2 down into the combined sorted array. We will increment the indices of lower and combined sorted array. Similarly, we can compare numbers 3 and 7. Since 3 is less than 7, we can copy 3 down into the combined sorted array. Thus, we will increment the indices of upper and combined sorted array. Again, we will compare numbers 5 and 7. 5 is less than 7. we can copy 5 down into the combined sorted array. Then increment the indices of upper sorted array and combined sorted array. In similar fashion, we will compare numbers 18 and 7. 7 is less than 18. We will copy down 7 into the combined sorted array. Then increment the indices of lower sorted array as well as the combined sorted array. This time we will compare numbers 18 and 12. Again, 12 is less than 18. Therefore, we copy down 12 into the combined sorted array. Then increment the indices of lower and combined sorted array. This time we compare number 16 from lower and number 18 from upper sorted array. Since 16 is less than 18, we can copy 16 down into the combined sorted array, also incrementing the indices of lower sorted array as well as combined sorted array. Again, we will be comparing numbers 18 from upper sorted array and 33 from lower sorted array. Since 18 is less than 33, we can copy 18 down into the combined sorted array. Similarly, increment the indices of upper and combined sorted array. This time we will compare numbers 21 from upper sorted array and 33 from lower sorted array. Since 21 is less than 33, we can copy 21 down into the combined sorted array, thus incrementing the indices of upper sorted array as well as the combined sorted array. Again, we compare numbers 24 from upper sorted array and 33 from lower sorted array. Since 24 is less than 33, we can copy 24 down into the combined sorted array, at the same time incrementing the indices of upper sorted array and combined sorted array. We will be continuing until we have passed beyond the limit of one of the two sorted arrays. After this, we simply copy over all the remaining entries into the non-empty array. If we take a look at the example where the upper sorted array has the numbers 1, 3, 7, 9, 14, 15, and 21, and your lower sorted array has the numbers 2, 10, 12, 19, 23, 25, and 28. Once the upper sorted array is merged completely into the combined sorted array, for the lower sorted array, we have a partial leftover with numbers 23, 25, and 28 still needs to be merged with the combined sorted array. Thus, we simply take those numbers and put them into the combined sorted array, having the same sequence. Running time for the merging algorithm is order n. As mentioned before, merge sort is a technique used to recursively sort the left half, recursively sort the right half, then merge the two sorted halves. This merging of two sorted arrays, we have seen how it's done in our example. Now remains the programming aspect of it. It is being assigned as homework. Go through the merge code provided in your book as well as in your lab. Try to understand the coding aspect of the functions in and output arguments. Run the code multiple times with different inputs apart from the input given on the slide.